Now, one important point to remember is that this calculations for derivative calculations, like I want to do central difference schemes for every I had to do this this minus twice this plus that. Okay, and I can do it in a loop. But if you do in a loop, if you do it in a loop, then it is more expensive. So idea is to do vectorization. So you can take the whole array and subtract from the whole array. Okay, so array minus array subtraction. Okay, so we did this in the past. So if you have array A and you say array minus B, and array A minus B of the same size, it's much faster than doing a loop AI minus BI in a loop. Okay. So this is preferred, is vectorized. Okay, and more optimized, or is faster, because it's a vectorized operation where many operations can be done in one cycle. Okay, you should always use vectorized operations if you can, and we can do it for finite difference. How do I do it? So my array is here 5, 0 to 5 n minus 1. But for doing the derivative calculations, remember, for this one, I can just take the left point and right point, central reference scheme. I need only 3 points. Okay, great. For 5, 1, I need this point and this point. Okay, 5 requires 5, 0, these 2 points. This one. 5, 0 requires which one? 5, 0. 5, 0 requires 5, 1, and one left point of 5, 0. And what is the left point of 5, 0? With periodic boundary condition, the left point is 5 n minus 1. Okay. If you recall, I had 5, 0, 5, 1, and this 5 n minus 1. Okay. So I need this left point. So if I have vectorized, then I need to have that point to the left. So idea is that we save this 5 n minus 1 to the point to the left of 5, 0. Okay, so this 5, 0 is 5 n minus 1 sitting here. Similarly, for 5 n minus 1, I need 3 points, and so left point is available. It's 5 n minus 2, but point to the right is what? This 5 n minus 1. So left point will be that. To the right is 5, 0, and 5, 0 is sitting here. Okay. So we make a copy. We make a copy here. Okay, 5, 0. So we add 2 additional points in the array for central difference scheme, one to the right and one to the left. And left point is 5 n minus 1, and right point is 5, 0. And if we have this, then we can easily vectorize. Okay. So if you look at it, my real implementation, my real array is going from f0 to fn plus 1. Okay, and f0 contains 5 n minus 1, and fn plus 1 contains 5, 0, and f1 contains 5, 0 actually. Okay, and we need to copy. After the step, you just make sure that this value here is same as this value here. This arrow is the same, and this value is same as that value. Okay, so let's look at the implementation. So in some, well, I mean, this is just straightforward if you keep in mind. I set zeros of size n plus 2, right? So the 0 to n plus 1, then n plus 2. And okay. So I'm using RK2, okay? So that's why I have F mid for, say, mid, intermediate step. So this is what you should keep in mind. So initial temperature or initial function is 1 to n plus 1. So 1 to n plus 1. Yes. Well, n plus 1 means I go up to n. Okay. So this is n plus 1. And 5, 0, which is F0. So F0 is temp minus 1. So I take this value, temperature. So the real one. The end point is copied to the leftmost point here. The end point is copied here. And n plus 1, Fn plus 1 here, this one, has a value of the temperature at leftmost point, which is initial temperature 0. Okay. So we need to keep doing it all the time. In fact, we see that here. This one, F0 is Fn and F minus 1 is F1. Okay. So, and you can see that central difference scheme is here. Okay. So what I'm doing in this step, so F1n plus 1. So I have this full array. So so this is midpoint, 1 to n plus 1. Okay. So what do I write? F I plus 1 minus 2 Fi or Fi plus Fi minus 1. Okay. I minus 1 in this one. So minus 2, the central array, which is I take part of the array. So this is beauty of Python. We do not need to worry about full array, but we can take part of our array slicing. We can do that. For this is 0 to n, which is which one? I minus 1. This is I minus 1. So take the middle part. The second part is this one, 0 to n minus 1. This one. Okay. I take this bit. So I'm multiplying this. This part is this one. This part is in fact this guy here, and 2 to n plus 2, which is the right part. If I plus 1, which is 2i plus 1, is this one. So in one shot, I'm doing the subtraction for all the points. Okay, 1 to n plus 1. Okay, I'm computing the second derivative at all the points in one shot. Okay, and this is fast. Okay, so this is for f mid, and of course we need to copy all the time. So this operation is exactly the same as what is done there, and so on. Okay, so yes, so second derivative we need to compute by vectorization. That's the key. Okay, I hope it is clear to everyone. Just vectorize is critical for FD scheme. Just need to do it. Okay, for getting overcoming this limitation or the requirement for tiny delta t, for kappa large, my delta t can be too small kappa. So we can use a semi-implicit scheme, right? So here, instead of computing at derivative at n at time using at tn basically t, I can also compute at t plus delta t. Okay, so the second derivative is computed not only using a value of the function at t, but also at t plus delta t, which is not available right now. Okay. So we do it like that. Okay. But it turns out we can just reassemble it. Okay. So reassemble it. So it comes to the left. And so reassemble it, then we get, in fact, equation of this sort. So phi n plus 1 to the left hand side and phi n to the right hand side. And this is it turns out if you look at structure, so left hand side has the matrix of the form this. Okay, so these are known. And right hand side, given value of the function at time t, I can compute the right hand side. So this is known. R0, R1, R2 at each point. So I'm using periodic boundary condition. So 0 to n minus 1. And so here you can look at the structure. It is I. So space point, this is I part. This is I plus 1, which is to the right. So if matrix multiply, 5, so this will multiply with, let's imagine here, that's for second row. Phi 1 here, this will be phi 0, and this is phi 2. Okay. So the right side is minus kappa delta t by 2 squared, prefactor, which is y. So y equal to minus kappa delta t by s squared. And what is x? X is 1 plus kappa delta t by s squared. Okay, and it turns out these two are exactly the same, one to the left and one to the right. So we have y, y, and x. Okay, so it's a tridiagonal matrix. So there's a diagonal element which is x, and there's one above the diagonal element and one below the diagonal element. And of course, at the Is periodic boundary condition. So at 0 and the last point, we have this anomaly, and we need to worry about it. Okay, so I have not covered right now how to solve a tridiagonal matrix, but we will do it at the end. It is doable. Okay, but the semi-implicit scheme has this issue. It's, uh, it's a bit tricky how to solve a tridiagonal matrix, but it's not very difficult. Okay? So once you know how to solve tridiagonal matrix, I can get phi's. For arbitrary delta t, we don't need to use a tiny delta t like that. We can use pretty large delta t. Okay. Okay, so this is a diffusion equation using finite difference.